Alright, so this last set of notes for Unit 5, we're going to finish up talking about molecules, specifically looking at how the shape of the molecule determines the polarity of the molecule, which in turn determines the properties of those particular molecules. So let's go back and review a little bit what we know about electronegativity. If you recall, electronegativity is the relative ability of an atom to attract electrons in a chemical bond. And this chart that's given to you in your notes gives you values for electronegativity for all the elements, not including noble gases, because if you remember, noble gases don't bond with things, so they're generally not included in charts of electronegativity. Now, I know we've seen xenon in some of our molecules, and yes, it's kind of an exception because it's so big, it will actually bond with very electronegative fluorine. And if you remember our trend, electronegativity increases as you go across, decreases as you go down. So fluorine will have the highest electronegativity. All right, so when we're looking at atoms bonded together, a chemical bond is really never completely ionic or covalent. Remember, ionic bonds, we say electrons are gained and lost. Covalent bonds, electrons are shared. So the bond character depends on how strongly each atom attracts electrons, meaning it depends on the electronegativity of the atoms. So if we have two identical atoms bonded with each other, like here we have fluorine bonded to fluorine, they have equal electronegativity, which means their electrons are shared equally between them. We call that a nonpolar covalent bond. When electrons are shared equally, as you can see in this picture, all that electron density is equally distributed between the two fluorines. That is a nonpolar covalent bond. That is true sharing of electrons. And that only really happens when two identical atoms are bonded with each other. If electron pairs bond between two different elements, then they might not be shared equally. If the electronegativity difference is between 0.4 and 1.7, we consider that a polar covalent bond. So here you can see fluorine is more electronegative than hydrogen, so the electrons are more dense around the fluorine than they are around the hydrogen. They're still sharing, it's kind of like a tug of war, but fluorine is pulling on them more. It's more attracted, the electrons are more attracted to fluorine, so they are shared unequally in a polar covalent bond. And then if we end up with a large difference, which is a difference above 1.7, we can actually remove an electron and transfer it from one atom to the other, which is what happens in an ionic bond. So here you can see we actually transferred an electron from the sodium to the fluorine because of the big difference in electronegativity, and then those ions would bond with each other. So this chart that's in your notes summarizes the difference in electronegativity. So you look at that very first table, find the electronegativity value for each atom in the bond, subtract them, and then wherever the difference falls tells you what kind of bond is likely to be formed. Okay, so if they're the same element, it's a nonpolar covalent bond. If they're very close in electronegativity, it's mostly covalent, meaning they're mostly shared equally. If the difference is between 0.4 and 1.7, it's a polar covalent bond, so they're shared, but one is pulling more than the other. And if the difference is greater than 1.7, it's mostly ionic. One electron will be transferred from one atom to another. Okay, so let's look at an example here with HCl, hydrogen bonded to chlorine. So when we look at our chart at the very beginning of our notes, we find that chlorine has a value of 3.16. Hydrogen has a value of 2.20. We subtract them and we get 0.96. And then if we go back, you can see 0.96 falls in the polar covalent range. So that means the electrons are actually going to be pulled towards the chlorine within the bond. Now, this symbol right here is a Greek letter, delta, and delta means partial. So since chlorine is pulling the electrons towards it, it has a slightly negative charge, a partial negative charge. Hydrogen has the electrons being pulled away from it, so hydrogen will have a partially positive charge. And when the electrons spend more time around one atom than the other, resulting in these partial charges at the end of the bond called a dipole. So when you get a partial positive, partial negative, that is called a dipole when the charge is all concentrated on one end of the bond. Okay, now, like we said before, bonding is not often clearly ionic or covalent. It kind of varies depending on the difference in electronegativity. So what this chart shows us is a bunch of compounds and their difference in electronegativity is plotted, and then on this axis we're looking at the amount of ionic character. So the bigger the difference, the more ionic it's going to be. And this curved line is a trend line, so it kind of follows the general curve of our plotted points, as you can see here. So let's label on the graph where the different types of bonds are going to fall. Okay, so we said if we get up to a difference of 0.4, which is going to be right around here, okay, so from 0 to 0.4, this is going to be our non-polar region. All right, and then we said in the region from 0.4 up to 1.7, which is about right here, that region is going to be the polar covalent region. And then above 1.7, that's going to be our ionic region. And as you can see, the amount of ionic character increases as we go up. So the bigger our y-axis, the more ionic the bond is, meaning the more the electrons are transferred from one to the other. So let's look at our questions here. What is the percent ionic character of a bond with a difference of 2.0, meaning electronegativity difference of 2.0? So electronegativity difference of 2.0 would fall right here on our graph, and we can see that that would be between 0.5 and 0.75, so maybe 0.62, which we could say is 62% ionic. Okay, and then where would LIBR be plotted on the graph? So if you go all the way back to the beginning of your notes and we look at that table, we find that bromine has an electronegativity of 2.96. Lithium has an electronegativity of 0.98. So when we subtract those two things, we get a difference of 1.98. So our difference, 1.98, would fall right about here, so that's where LIBR would fall on our graph. Okay, now we've looked at individual bonds and how they are nonpolar, polar, ionic, depending on the difference in electronegativity. Now we want to look at an entire molecule. If we have an entire molecule with covalent bonds in it, those molecules are either polar molecules or nonpolar molecules, and the polarity is dependent upon the shape. It's dependent upon the geometry, whether it's linear, trigonal planar, bent, whatever it happens to be. That's going to tell us whether or not a molecule is polar or nonpolar. So we're going to look at two examples. We're going to look at water and carbon tetrachloride. All right, so if we're going to draw the water molecule, water, of course, is H2O. We put the O in the middle, single bond to the hydrogens. We're going to end up with two lone pairs on the oxygens. You should know how to draw dot structures to get to this point. And then when you look at the O, it has two bonds, two lone pairs, which makes it a bent molecule. If we look at carbon tetrachloride, CCl4, we put the carbon in the middle. We're going to single bond the 4 chlorines. we're going to end up with 4 bonds, no lone pairs around the carbon, which makes it tetrahedral. Tetrahedral. Okay, now, if we think about the individual polar bonds, here, oxygen is more electronegative than hydrogen, so all the electrons are being pulled toward the oxygen in both of those bonds. So that's going to leave the oxygen here with a partial negative charge and both hydrogens with a partial positive charge. So you can see we have a negative side of the molecule, a positive side of the molecule, which makes this a polar molecule. Now, over here, because there are no lone pairs and all the bonds are going in opposite directions, they're all going pulling towards the chlorine in all 4 different directions, then there's not going to be an overall negative and positive side of the molecule. They're all going to cancel each other out. All of those dipoles are going to cancel each other out, which makes carbon tetrachloride a nonpolar molecule. So what we're going to talk about in class is how to look at a shape and know whether that geometry is polar or nonpolar based on its structure. So what you're looking for is some sort of asymmetry, something where you have like a bent structure where all of the electrons are being pulled in one direction versus a very symmetrical structure where all the electrons are being pulled in opposite directions and they're not all going to end up on one side of the molecule. Alright, so the last quick little thing is the solubility of molecular compounds, and it all depends on the polarity. Polar molecules and ionic substances are soluble in polar liquids, which is water. Water's polar. Nonpolar molecules are soluble in nonpolar liquids. So the term like dissolves like means polar things dissolve in polar things. Nonpolar dissolves in nonpolar. So when we did the lab and we were looking at properties of sugar, which is sucrose, you notice that sucrose dissolves in water. While sucrose also had a low melting point, which tells us it's molecular, but because it dissolves in water, we know that the sucrose molecule is polar. Wax is also a molecular compound, but it did not dissolve in water, which tells us that the molecule that makes paraffin wax is a nonpolar molecule. So the polarity is going to tell us a lot about the properties of those particular molecules.